This is ECE 341 Random Processes. This will be part 1, lecture 3. So last time we finished up a lot of our initial discussion on sets. Today we'd like to go ahead and move our investigation into probability. I think we'll start this with a coin flipping experiment. There are two outcomes from a coin being flipped. It can either be heads or tails. We'll indicate these two events using an H or a T. And what I'd like you to do is I'd like you to think about a sequence from this coin flipping experiment that ends up in the following pattern. It gives us H, T, T, H, 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 T, 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 and then I'm interested in what happens next. I'd like us to be able to try to figure out what goes into that next box. I think trying to figure out how to answer this involves lots of possible different approaches, and we're going to look at quite a few of them. So we certainly could say that the next box was either definitively an H or a T, but that really does suggest some perfect confidence in the answer. And there's something about this experiment, this idea of a coin toss, that suggests some uncertainty that we wouldn't really know what the future holds for us. In that kind of a situation, and others like it, it might make a lot more sense to describe the next element in terms of a probability, something like a probability of a head occurring or a probability of a tail occurring in that tenth element of the sequence above. So let's look at some approaches to thinking about this sequence again. They went heads, tails, tails, heads, 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 tails, 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 and then what came next, and see if we can come up with, for example, a probability of head for this experiment. I'm going to introduce several methods that have been used or are used in trying to assess this particular probability, and we'll see that they can give us different types of answers. They have different type of assumptions involved in them. The first one I'd like to look to is what is just known as a classical. It's the classical method. It's a classical assignment of probability. So let's go ahead and think about this classical method of probability. Basically, in the classical method, an experiment, right? This experiment is going to be divided. It's going to be divided into equally likely outcomes. So in a real classical sense, we take our experiment and we divide it into equally likely outcomes. We can come from that then that the probability of some event A is going to be equal to the number of elements that are making up whatever that event A is. So NA is the number of outcomes in A, right? And then we will divide that by N, which is just the number of total outcomes. So let's explore this classical method using a couple examples. For our current one, right, what is our experiment? Well, there's two outcomes. There is a tail and there is a head, right? And so from that, we know that cap n equals 2. There's two outcomes. The classical method says that we will assign them to be equally likely outcomes. So if there's two outcomes, right, and each is equally likely, we would expect each of those to be of probability 1/2, right? They'd each have half the total probability. In this particular case, if I wanted to look at something like a probability of a head, let's go ahead and make that a head, that thing that we were trying to figure out the next sequence. So what's the probability of a head, right? We would say, what's the number of outcomes associated with a head over the total number of outcomes? In this case, the head is just one of those outcomes, right? And the total number is 2. So we would get a 50% probability, something along those lines. The classical method here would assign a likelihood or an outcome of 50%. There are some limitations to this. It doesn't work in every situation, but it certainly can work in many situations. We could extend this just a little bit more. We could think of something like rolling a six-sided die, right? Rolling a six-sided die, right? And then we could think of an event A as being equal to the outcomes at either a 1 or a 2 was rolled, something along those lines. And we could say something about, well, let's find out what's the probability of A. If I did that from the classical method, right, I'd say that this probability of A equals the number of outcomes in A over the total number of outcomes. Now, A in this case, we can see, right, a 1 or a 2, that's 2 of the different outcomes. And then because it's a six-sided die, the different outcomes, or each of those 6 ones, so n is equal to 6. That would give me a 1/3 in this particular case. So two very quick examples of the classical method. This is not the only way, of course, to think about probability, so let's look at another one. Let's go ahead and look at an idea that is called relative frequency. So we can look at what is called a relative frequency approach, relative frequency approach to probability. And this looks something like this. We repeat an experiment, right? We repeat an experiment n times, right? We count the number of occurrences in A, whatever our event A is, right? We could call that number of occurrences something like NA. And then we would know what? We would know that the probability, right? We could have this probability of A, right, is equal to something like the number A over N. Now, I suppose if we were going to do this in maybe a really rigorous way, maybe more ideally, we would do something like probability of A is a limit as n goes off to infinity. So you repeat this as many times as you possibly could and count all of those different occurrences in A. If we do it in a limiting process, we're going to keep getting a better and better estimate is what we would expect. But this idea of relative frequency, we usually don't have the ability to repeat that experiment an infinite number of times. So we get what we get, right? So let's think about it in this particular case. Again, with the coin toss experiment, I would like to know what is the probability of heads, for example, right? Probability of heads from a relative frequency standpoint says repeat an experiment some number of times n. Let's go back up to what we looked at here. If you look back at our original sequence, I had repeated that experiment, if you will, 9 times. I threw that coin 9 times. I got heads, tails, tails, heads, 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 tails, tails, tails. So I had cap n equaling to 9 in this particular case. The event I'm interested in is heads. If I count the number of h's in there, I see 4 of them. So n of h, right, the number of heads is equal to 4. If I was going to put this then into a relative probability standpoint, I would have the number of heads over the total number, which in this particular case is 4/9. And notice that that is not equal to 1/2, right? So for this particular sequence that I used, I'm taking a relative frequency standpoint. 4/9 is close to 1/2, but it's not quite equal to 1/2. From this kind of a viewpoint, based on the experiences that I'd seen so far with that particular coin, right, I would have less confidence that a head would be the next one in the sequence than a tail would be. So that's a different way for us to get some frequencies or some probabilities based on the relative frequency. There's another one that we can look at, and this one's probably dangerous, but it also has its own kind of unique characteristics that can be useful on occasion. And I'm going to call this one the personal probability, personal probability method. So we'll call this personal probabilities, personal probability. That we don't divide the experiment up into equally likelihood. We aren't really doing a formal set of experiments where we take out the relative frequency. Really what we're doing here is we're going to assign a probability based on some expectation or personal experience. We as humans do this actually quite a bit. We run our lives and do all the things, and we're constantly assessing risk or likelihood of things happening. If you're driving down a rural road in North Dakota heading home for the holidays or something like that, you might be running your personal probabilities as the likelihood that a patrol car is going to be there and deciding whether that's going to let you speed or not, something along those lines. So we are constantly making these sorts of assumptions. Let's think about other things on this. You might sit there on a personal probability and say something like, am I going to pass this class, right? Am I going to pass 341, right? You could base that somewhat on your own personal probabilities. It's unlikely that you're gonna have equal likelihood based on all classes. We know not all classes have equal likelihood of passing. It's probably not going to be something that you're going to do a relative frequency. That would be an expensive investment to have to take the class, 1,000 times and see how many times you passed it versus how many times you didn't. That would be prohibitively uh, expensive in the investment to get that number then. In this particular case, something like a pass stat, personal probability might tell you quite a bit. Our brains are pretty good at finding patterns, and they're pretty good at collecting information and helping us make informed choices. It can lead us down the wrong path occasionally, right? Let's take a look back at this other one and think of it maybe from a personal probability standpoint. If I look at this sequence, if I hadn't thought of these necessarily as H's or T's, let me try it this way. Let's put in a 0, a 1, a 1, a 0, 0, 0, 1, 1, 1. If I hadn't necessarily thought of this as a coin toss experiment, or maybe even if I did, my mind sits here and it looks at that and says, boy, I think I see this pattern. 1 0, 2 1s, 3 zeros, and I want to see that 4 1s. That 1 there in this case is assigned to a T. So there's this part of me that says I'm almost 100% sure if I'm looking for patterns, right, that the next element there is going to be a T. That might suggest something like the probability of head, right? So I might sit there and say that the probability that there is a head, at least on the 10th element, right, as being equal to 0, right? Because I think I see that pattern in there. I think we can all appreciate the dangers that might go on in something like this. There's times that you're pretty good at finding patterns, and then there's times that we see patterns where they maybe don't exist at all. There is another one, and this is really the way we are going to favor in this class as far as trying to find probabilities or setting up probability models. Oops, and I think I misspelled that, so let's go ahead and fix that. We're going to look at an axiomatic. We're going to look at an axiomatic approach to probability. And really what the axiomatic approach does is it has us assign, we're going to go ahead and assign event probabilities based on axioms. This approach has a lot of advantages. It allows us to set up or establish a framework of mathematics that can be expanded and made actually quite robust and quite flexible to address so many different situations. It is one that adheres to the basic principles of mathematics and allows us to move forward with a lot of certainty in the way our models can work. So for sure, at least in this class, we're going to be taking a more axiomatic approach. So let's go ahead and try to start this. This is all in chapter 1, by the way. So I think it's in chapter 1. It's that first chapter on the probabilities. Let's go ahead and take a look at these probability axioms. So we're going to go ahead and start that one. So we're going to go ahead and start taking this axiomatic approach. And I think the way that we're going to do it is we're going to first start out by coming up with the first 3 probability axioms. So let's go ahead and set up the probability axioms. We need a starting point, and just in case you are a little rusty on your definitions here, what is an axiom? An axiom is just a self-evident truth, okay? So a self-evident truth. What I hope is as we go through these first 3 axioms, there's only 3 axioms, and this is actually kind of surprising. With 3 axioms, with 3 self-evident truths, we can build incredibly sophisticated and incredibly powerful mathematical models for describing likelihood or probability. That will be part of my goal in moving us forward in the class, but it starts out with just a couple of axioms, 3 self-evident truths, okay? So let's go ahead and see what we can do on these. I'm going to start out by just saying let's start with a probability. I'm going to do a little bit of math notation here. So I'm going to look at a probability measure. Measure theory is a branch of mathematics. We don't have to get too hung up on it, but I'm going to talk about a probability measure P. I'm going to use a square bracket, and I'm just going to say it has some argument. So a probability measure P maps, okay, it maps events in our universe or in our universal set. It maps events in our S, right, to real numbers, such that these three axioms hold. Okay, so a probability measure just takes events and maps them to numbers. Okay, and it's going to map them to numbers according to these three axioms. We'd already seen some of that. I'd already used that kind of P notation before. We looked at something here like a probability ahead being 0. We looked at another one that said a probability ahead was 4/9 or a half. Both of these took an event, in this case heads, right, and they assigned it to a number. We didn't base it on axioms in those cases. But let's take a look at these axioms, these self-evident truths. Hopefully they will look self-evident to you. So let's look at axiom 1. Our axiomatic approach to probability is going to be based on 3 underlying axioms. The first axiom says something like this. For any event A, so for any event, well, I'm not doing very good in my spelling here, so any event A, so for any event A, right, the first axiom says that the probability of A has to be greater than or equal to 0. Negative probabilities are meaningless. That's what the first axiom says. It doesn't make any sense to have a negative probability. I certainly don't know what that means. Probabilities, right? A 0 would mean that it never happens. And it would keep going up, and as we would expect, once we get to 1, we're going to take that number as a fraction of likelihood. 1 would be perfectly likely, right? So this idea of an event A, something that could happen in our universe, it can't have negative probabilities. Seems pretty self-evident, right? Axiom 2. What does axiom 2 say? Axiom 2 says something like the following. The probability of being in our universe, right? Our universe is all the things that matter to us. It's all the things that can happen. And if we're just saying, what's the chance that we're in our universe? That should be 100%. Whatever you do in your experiment, something that comes out has to come from that universe. The probability that something came out of that universe, that we have that universe, is 1. So it kind of puts an upper bound on these probabilities as well. That's our axiom 2, self-evident again. The likelihood of everything, right, is 100%. Axiom 3 is where things get a little bit interesting, at least in my mind. So we'll look at axiom 3. And remember, once we have these 3 axioms, it's just with these 3 and then some logical arguments that we're going to be able to develop far more sophisticated and far more interesting models to deal with a lot of situations that we might encounter. So axiom 3 looks something like the following. And this is where we need some of that language we had developed in those earlier lectures. For accountable, that just means we can count it. Could go out to infinity if you want, but for accountable, mutually exclusive, that means there's no overlap between these elements. So for countable, mutually exclusive events, A1, A2, A3, just the fact that I'm subscripting these with an integer tells me that it's countable. So I have some event A1, A2, A3 going out to potentially A infinity. Each one of these guys taken pairwise are mutually exclusive. That means their intersection is equal to the null set. Well, then what? The probability of A1 union A2 union going on forever, right? If we union all those guys up, that is going to be the probability of A1 plus the probability of A2 plus, and we can keep going on forever. In other words, if I have mutually exclusive things, right, and I want to know the likelihood that the group of them occurs, I can just add up their individual probabilities. It's really important in this particular case that they be mutually exclusive, that they have no overlap in stuff. I can re-express this maybe with a little bit more compact notation. I like this compact notation better. This basically says the probability of a union going 1 to infinity of my AIs, right? This big group of events, mutually exclusive events, is equal to a summation I equaling 1 to infinity of the probability of the individual pieces, something along those lines. Okay, so those are our 3 axioms, and I hope this one makes some sense as well. Think of something like a 6-sided die experiment. The universe is 1, 2, 3, 4, 5, 6, something along those lines, right? If we were going to talk about those events, 1, 2, 3, 4, 5, 6, those are all mutually exclusive. It says that if I want to take any grouping of those, like the probability that my die roll was 3 or less, that would be 1, 2, and 3. So probability that my die roll is 1, union with the probability of my die roll being 2, union with my probability of die roll being equal to 3. Those things, we could just add their individual probabilities. We know from our own experience before that a six-sided die is equally likely, right? And so we would have 1/6, then 1/6, then 1/6. Add those together, you would have gotten 1/3 in that particular, or 1/2 in that particular case. Half of the die rolls are 3 or less. That makes sense because 1, 2, 3 are half of the total outcomes in there, something along those lines. These three axioms should seem totally obvious to you, not requiring a proof. And in fact, that's really another part of this axiom. They are self-evident truths, and we do not need to prove them. We take them as being true. And then everything else that we can derive for our system is going to be based on these axioms and having some proofs. Okay, so let's look at a theorem that's related to this. So I'm going to look at a little theorem on here. I'm going to say something like the following. If there's an event A that is A1 union A2 union all the way out to, let's go to AM, where M now ends. It's not going out to infinity. And I have AI intersect AJ equaling the null set for all I not equaling to j. That means I've got M objects A1 through AM that are mutually exclusive, right? I can say that the probability of A is equal to a summation I equaling 1 to M, don't have to go out to infinity, of the probability of AI. The book does a nice job of talking about why this is slightly different. In fact, my last example was more like this case of this theorem, why this particular simplification, not going out to infinity, still works, and why it is different. Let's think a little bit, though, about how we might prove it. Not terribly difficult proof here. So if I wanted to do something like a proof on this, we would start by using axiom 3. So we'd start with axiom 3, which says we're going to go out to infinity, right? Something along those lines. And we would let something like, and we would have something like, in this particular case, that this AI is equal to the empty set, something like that, for I greater than M. So we could have our originals, A1, going all the way out to AM, right? And then we would have our AM plus 1 going out to infinity, where each one of those guys was an empty set. I could assign empty sets to each one of those particular ones, right? Axiom 3 says what? It says that we should be able to add all of these probabilities up together because we're all mutually exclusive. The empty set is mutually exclusive from anything else. We could certainly work on that. How do we work with that? If you think about something like an A1, right, unioned with nothing, that is equal to A1, right? Because we know nothing adds it. And if I take A1 intersected with nothing, that's equal to nothing. That tells me that these two guys here are mutually exclusive. So the empty set's sort of an interesting one. It can be mutually exclusive from anything else, right? Including itself, which is sort of strange. So I've got a set of mutually exclusive guys. I can get their probability by adding them all up. And what do I know? What is the probability of nothing happening? What should we be able to get on that? Well, certainly that should be equal to 0 in this particular case. How can I get that? Well, you could think about something like this. You could sit there and say, I could look at what is the probability of S. We already know that from axiom 2. That's equal to 1. Well, that's also equal to the probability of S, right? Unioned with the empty set, unioned with the empty set, going on forever. You could do that sort of stuff. This is related to axiom 3. I can create my A's here. A1 is S, A2 through A infinity are all those empty sets. And that creates a mutually exclusive set of sets, right? So I know that that probability is the probability of the sum of each of those. That's probability of S plus probability of the null plus the probability of the null going on forever. This probability of S is equal to 1. That 1 cancels with this one, and we're left with something like this. 0 equals the probability of the null set plus the probability of the null set plus going on forever, right? But the probability of the null set has to be what? From axiom 1, that has to be greater than equal to 0, right? And we've got a whole bunch of them. Divide it through, we can get probability of the null set equaling to 0. The only way you can take non-negative numbers and add them up all the same number, in fact, it wouldn't matter if they were negative or positive, the only way you're going to get a bunch of numbers all added together to give us 0 is if it was 0 to begin with. So very easy to kind of put in the details on this. If I want to go back to this original one where I was looking at this extra theorem, if I want to go out to a case that is not going to infinity, right? It doesn't matter. I don't have to go to infinity. The way I could prove it is just by, say, take that set of 1 through m, let the rest of them all be the empty set, something along those lines, go back and use axiom 3, and because of some other developments we did all based on the axioms, we know that those extra pieces are not only mutually exclusive, but they have individual probabilities of 0, and from all of that we get back to this result, something like that. These can get kind of tedious in some ways, but once we've established the rules, then we don't really have to come back to them later. So we could make this go down to an m equaling 2. So for example, so note, right, just for m equaling 2, right, we could have something like this: probability of A1 union with probability of A2, right, is probability of A1 plus probability of A2. If I have two mutually exclusive items, the fact that they are mutually exclusive just means I add their probabilities. I could certainly change this just slightly, and this might look a little more familiar. Probability of A union B, right, as long as A intersect B equals the empty set. So as long as they're mutually exclusive, I just add their individual, right, probabilities, something along those lines. So all of this, I think, at this point is not terribly surprising. We started out with 3 axioms, 3 self-evident truths, and then we built a very simple theorem. Again, this is in the book, that just let us look at a little bit more restricted or specialized case of the third axiom. And we can continue with this. We can continue building a lot. So consider the following as an example. Let's look at the case of equally likely outcomes. Let's look at the case of equally likely outcomes. Now we're using additional information. We are sitting there saying that we have an experiment where we have a set of outcomes possible, and they're all going to be equally likely. How could I start beginning to get some mathematical description of that? I have a universe, right? That universe is divided into mutually exclusive, finest grained, events. We've done this before. So I might think of something like an S1 going all the way through, and I probably shouldn't make that fancy S. Let's just make it a little S. S1 going all the way through some Sn. So I've got n outcomes, and we're going to assume each, right, this is just an assumption based on the facts of our particular experiment, each Si is equally likely. What we're going to find by doing this, if we use our axiomatic approach, we had our first 3 axioms, we can augment that with the facts on the ground for us, whatever is reflective of our experiment. We're looking at this case where I've got a universal set that contains a set of n equally likely outcomes, and we would like to be able to figure out then what the probabilities are associated with that. So I think out of this, what we should be able to get is that the probability of any one of those outcomes is 1 over n. How do I get that? Well, I know that the probability of S, right, from axiom 2 equals 1. So that was axiom, let me try this again. This is axiom. That was axiom 2, right? Probability of everything is equal to 1. We also know that each one of these guys, we're letting these guys all be mutually exclusive pieces in there. And we can look at that theorem we just covered that was a consequence of the third axiom plus a few squiggles. And we end up getting this being equal to the probability of S1 plus the probability of S2 plus going all the way out to the probability of Sn, right? But each one of these guys is equal. So I know that this one, right, is equal to this one is equal all to this one, which I'm just going to call the probability of Si, right? Or we could say it in a different way, that the probability of Si is equal to some constant k for all I, something along those lines. So what can I get out of that? I'm going to have 1 equals go ahead and put that in. I could write it as probability of SI plus the probability of SI. I could put a K in there if you wanted. It doesn't really matter. All the way out to the probability of SI, just pick it. And how many different copies are in there? There's n copies. So if I add n things up, I'm going to get n probability of SI. We know that's equal to 1. Solve for this. Probability of SI equals 1 over n. That's that equally likely kind of idea. We had talked a bit about that in the idea of a classical approach to probability. So we can accommodate the classical approach to probability, right, through the axiomatic approach, taking those 3 axioms in addition to having an experiment that's broken up into equally likely events. So this axiomatic approach, it really provides a mathematically strong way of being able to develop models. They all start with those first 3 axioms, and then we might make some additional developments based on conditions that reflect our particular experiment. So if I go back to some particular examples again, so let's try this. I'm going to have an example in here, and I'm going to go ahead and look at a 6-sided die. So I have a 6-sided, and I'm going to call it a fair. So that means equally likely per side die, right? So what is the probability that my die roll has some value I where I equals 1 out to 6, right? What is the probability of any one of those particular outcomes coming in? Well, they're equally likely, so I know that the probability of S, right, equals 1 equals the probability of a 1 plus all the way out to a probability of 6, which equals 6 times the probability of any one of those, probability of I, because we know that Pi, right, from all of this, Pi is equal to a constant. It's a fair 6-sided die. And what we can get out of that is the probability of I is equal to 1/6, as we'd expect. This is something we're all familiar with. You roll a 6-sided die, you have a 1/6 chance of getting a 1, you get a 1/6 chance of getting a 2. As long as that thing's fair, we would get something along those lines. How about we twist this just a little bit? So I'm going to do the following example. Let's look at having non-equally likely outcomes for a weighted die. I need to have some sort of an idea about how it's weighted. So let's look at a loaded. We're going to look at what is called a loaded 4-sided die. With the probability of getting I dots, where I is going to go 1 through 4, is equal to some number. I'm going to call that W times I. This is for I equaling 1 all the way up to 4. In other words, right, the probability of whatever face you see is proportional to the face. A 1 is going to be less likely than a 4, right? A 1 is less likely than a 2, which is less likely than a 3, which is less likely than a 4. The 4 is going to be most likely, right, because 4 would give us I equaling 4 in there. So I could try doing this. I could say something like the probability of a 1 is equal to W, probability of a 2, right, is equal to 2W, probability of 3, I can enumerate it. In this case, it's pretty easy just because there's so few outcomes, and probability of 4, right, is going to be equal to 4W. I know adding all these guys up together, adding these things all up together, this is part of our axiomatic approach, where the total number of outcomes that I've got are 4. They're all mutually exclusive, so I can just add up their probabilities. That does give me probability of S, which I know is 1, and then I add up the other side. What do I get? 4 plus 3 is 7, and 2 more is 9, and one last one is 10, so that's going to be 10W. I can solve for W there. W equals 1/10, right? And what can I get from that? The probability of I is equal to I divided by 10, where I equals 1, 2, 3, or 4. If it's going to be really complete, I'd say 0 otherwise, something like that. So the likelihood of me getting a 1 is 1/10. The likelihood of me getting 2 is 2/10, right? Likelihood of getting a 3 is 3/10. and the likelihood of getting a 4 is going to be 4/10. And notice that all of those probabilities do have to sign up or sum up to 1. That's a consequence of the second axiom. All of those probabilities are greater than or equal to 0. That's a consequence of the first axiom. And we can add them up because they were mutually exclusive, right? You don't roll a 1 and a 2 at the same time. They have no overlap. A 1 happens or a 2 happens, but not both or any part between them shared. They are mutually exclusive events. We did interject in this particular case this idea that our die was weighted. We might need some information on that, but once we do that, we can apply it within the context of those axioms, and we can get a very definitive idea of likelihood. Okay, so we will try to get just a few consequences of these axioms down. There's a way of expanding or extending our kind of knowledge of probability just by working with the original axioms and some logic, if you will. So let's look at some consequences. Consequences of the axioms. And these consequences of axioms, some we've already seen partly, okay? So consequences of these axioms, we're going to say that probabilities, right? This probability measure P will satisfies the following, okay? The first one, and we've already dealt with this, so I'm not going to go through any kind of proof on this. The probability of the empty set is equal to 0. So you could almost see this as kind of a connected one, particularly to axiom 2. The probability of the whole universe is 1, and the probability of nothing is 0, right? It still conforms to all of our axioms. In fact, we derived out of it from our axioms earlier, and it's just an extra piece that came as a consequence of the axioms. We'd already proven that one. How about this one, B? What is the probability of a complement? If I want to think about what's the probability of some event not happening, I'm going to say that this is 1 minus the probability that the event happens. How might I prove this? How might I know this? Well, I know that S, right, can be created into a set that involves A and A complement, right? Those two together give us everything. You could do that Venn diagram, right? You could have our universe here could be A, right? And then everything outside of that guy, that is A complement. If you intersect those two guys together, right? We know that, not intersect, if we union those two together, we know that we get S. So maybe that's a little better. S is equal to A union A complement, right? And we know that A intersect A complement, just by the definition of what complement means, is equal to the empty set. So a really simple way of constructing a universe, right, in terms of some event A is between A and A complement, something along those lines. Now, if I want to know what the probability, right, of A union A complement is, because those are mutually exclusive, I know I can just add them together. That's going to be the probability of A plus the probability of A complement, something along those lines. And I knew this was just S, so that is the probability of S, which we know to be equal to 1. So 1 is equal to probability A plus probability of A complement. Solve that guy for probability A complement, right? And we get that consequence of the axioms, 1 minus probability of A. Why is something like this useful? Well, oftentimes it's easier to compute out a complementary probability than the probability of some event. And so if I'm interested in probability A, but it's a lot easier to compute probability A complement, find probability A complement and just back out your probability A through this consequence of the axioms that PA complement equals 1 minus PA, something along those lines. Here's another one. I'm not going to probably prove this one. I'm going to call this one C. I'm going to take a look at this idea that if A is contained in B, right? That means B is the bigger thing, or A is no larger than B, right? A is fully found inside B. Then what do we know in terms of their probabilities? Then we know that the probability of A, right, is less than or equal to probability B. If B has got at least everything that A has, right, the probability of B has to be as large as, or larger, right, than the probability of A. So I think that one's a pretty natural one. The last one that we're going to do here, the fourth consequence of the axioms, is a little bit more involved, and so we'll spend a little more time trying to work our way through on a proof on it. But it really does expand us in an important way. So let's take a look at the following. Let's look at this case of having two events. Let's look at any events A and B. And I want to know something about the probability of A union B. Now, you might look at this and say, okay, that looks a lot like what we had seen before when we worked our way down to just a case of two things, right? We looked at the probability of A union B as being A and B individual probabilities added together. But it had a requirement there, right? It had a requirement that A was mutually exclusive from B for me to just get the simple sum of those two guys. Here I'm sitting and looking at a case of any two events, A and B, and they do not have to be mutually exclusive, okay? So if I look at these guys, because I said there's that any in there, they are not required, right? Not required to be mutually exclusive. So what do we say about the probability of the sum? Well, the consequence looks something like this. I'm going to write down the result and then we'll prove it. Probability of A union B is equal to the probability of A plus the probability of B, but then we have to make a correction of probability of A intersect B, okay? Something along those lines. I can show this with a Venn diagram, which isn't really a full proof. We will prove it with set theory here in a second. But if I was just going to do this in a Venn diagram, I think it's a pretty nice way of just at least getting some sense for it. Let's go ahead and draw our universe in here. So I'm going to go ahead and put in our universe in this particular case. I'm going to go ahead and draw that rectangle. I'm going to have a couple events, A. And, well, if I had started up earlier in the consequence where they were mutually exclusive, my B would have to be completely separate, right? It'd have to be not connected or overlapping with the first one. So here's my A. But we said it could be any, so we're going to allow there to be potentially some overlap. I'm going to show those two things, A and B, with some overlap. What does this probability say? So I'm going to look at probability A. That's the stuff I'm going to do in green, right? Something like this. So we're going to get all the probability associated with that. I'm going to go ahead and look at the probability of B. I'm going to do that all in this red, right? And what do I see? When I add A and B together, because there was some overlap, right? There turns out to be, in this particular case, some overlap, which I'm going to just show now is that little football shape, something like that. That guy got counted twice. So what do? We subtract it out, right? So we added all of A, we added all of B, but when we added B, that kind of doubled the amount that was common to both, and so we need to get rid of that common amount, something along those lines. So let's do a proof of this just to show the nature of these kind of proofs so that we can prove this in a more mathematical sense. So I'm going to do something like the following. I'm going to say my proof looks like the following. I'm going to create an event C, which is equal to B intersect A complement, something along those lines. If I look at A now, intersected with C, I get the empty set. I will try to show some basic diagrams as we go along. So if I look at my universe in here, and we had our A, right? And B was just all of B that was common to A complement, but not to A. I could draw it like this. So my A was that first circle, and C is just all that part of B that was outside of A. What I've done in this way is I have made a new item, C, that includes all the parts B that are not part of A, right? And A and C are, right, these guys are mutually exclusive, okay? And we know something about mutually exclusive stuff, right? So I know, for example, that I have this idea that A union C is equal to A union B intersect, right, A complement. That's just using my definition up there, which if I distribute this guy through is going to be A union B, right, intersect A union A complement, right? But what's A union A complement? That's just S. S intersected with anything is just the anything. So this is A union B. So A union C is the same as A union B, right? From this, I know what? I know the probability of A union B, that's what I was trying to start with, is the same as the probability as A union C. But what's nice about this is that because A and C are mutually exclusive, from axiom 3, I know that this is probability A, right, plus probability C, which I know is probability A, plus I'm going to have now the probability of B intersect, right, A complement. I have just a little bit more work to do on this, so I'm going to look at an additional bit. So I'm going to say, but I know that B is equal to B intersect A complement, right? Union B intersect A, okay? If you wanted to work that through, you could distribute this whole guy across. That would be what? That would be B union. It's kind of that distributive rule in reverse of A, right? Intersect A complement. That's B union the empty set, which equals B, exactly as I wanted it to be. Okay, so if I know that B is B intersect A complement union B intersect A, I know that the probability of B is equal to probability of B intersect A complement, right? Plus probability B intersect A. Because those two guys were mutually exclusive, I can again use the third axiom and just write it out as a sum of those two pieces. Well, that first piece, B intersect A complement, that was just the probability of C, right? So I've got my probability C there, and I'm going to then add into it probability of B intersect A. And what does this do for me? I can solve this whole thing for probability C. Probability C is equal to probability B minus probability B intersect A, right? So what can I do with this? I'm looking for an expression that I just did of probability C. I had the thing that I was interested in, probability of A union B, and it was in terms of a C being added to A. So let's just put all those pieces together. So I had probability of A union B. I was trying to do this for arbitrary events that were not necessarily mutually exclusive. Said that was probability of A, right, plus probability of C. But I just came through this idea that probability C was equal to probability B minus probability A intersect B. And now I'm done, right? Okay, so it's a little bit, you got to keep your wits about you, have a little bit of detail orient when you go through and do these set operations to prove it, but that's exactly what we wanted to show with this. This is one of those ones that comes out as a consequence of the axioms, and once we know it, we don't have to go through all of this again, we can just use it. So we started with 3 axioms, right? 3 self-evident truths, and now we're building more complex models based on that. Let's quickly do a generalization of this, and then next time we will do some examples based on this and others, and also introduce another idea called conditional probabilities. But for now, let's talk about a generalization. Let's generalize D. So these were all consequences of the axioms, and I would just like to generalize this. So a generalization of this guy might look something like this. For some events, AI, right, where I equals 1, 2, and going on to infinity, okay? No requirement, not required, right? Not required. Whoops, that's not what I wanted. Not required. These guys are not required to be mutually exclusive. Okay, so there's no requirement of mutual exclusivity in this. The probability of the union I equaling 1 to infinity of AI is equal to a summation I equaling 1 to infinity, probability AI. I don't even know that this is in the book, so this is a little extra piece. Minus then the probability of AI intersect BI. Let's put that all as part of that sum piece, right? Which we know is less than or equal to the sum of just the probabilities. Because those overlaps, if they're present, would only increase the overall value. So probabilities summed here of the AIs. If I just add up all the probabilities and they had some overlap, right, you'd end up counting that overlap a bunch of extra times, right? And that would cause it to be greater than the true probability because we didn't do the correction in this second line, something along those lines. What are the B's though? I still need to define that. Where, I'm going to just say where BI is equal to a union, I'm going to do it on K, going from 1 to I minus 1. So this changes within the sum of the 8Ks. I'm just going to say, for those of you who maybe had some math background before, this is similar. This is a similar kind of process. It's similar to what is known in maybe one of your math classes as the Gram-Schmidt. This is like the Gram-Schmidt orthogonalization process. Okay, so you can, in this particular case, just use the overall expression that I've given you, that the union, right, of an arbitrary number of events that are not necessarily mutually exclusive, right, can be gotten by the sum of the probabilities minus some intersections. And those intersections are essentially subtracting out whatever had been double counted before. And to get that double counting right, we indicate this kind of auxiliary or extra piece BI, which is a union from 1 up to the 1 less than the current piece we had of all the AIs, something along those lines. Let me show very quickly a Venn diagram, then we'll be done today, of how this works. I'm going to do it for the case that is one bigger than what we had done before. So let me back up just for a second. What was D? D was this idea, right, that we have two events that might not overlap. We want their union. We ended up adding the two pieces together and then correcting by subtracting off the stuff that was overlapped. We have this nice Venn diagram of that. What I'm trying to do now is I'm giving you a process that allows us to do the union of more than just two, right? And again, we just add up the pieces, but we have to subtract off some corrections, and those corrections get a little bit more complicated than in the case of just two things. They turn out to be just a little bit more tricky. I'm going to go ahead and just do the next one up on this. So let's do as an example, right? As an example, let's look at the probability of A1 union A2 union A3. So this is one more element than what we dealt with before. This is three pieces all added together that are not necessarily mutually exclusive, and I want to know what they look like. If I look at the overall equation in here, I'm going to start out at I equaling 1, right? So I'm going to say, what is the probability of the union of all these things? Well, I'm going to start at the I equaling 1 term. That's going to be probability of A1 minus the probability of A1 intersected B1. But B1 is what? B1 is just a sum k equaling 1 to 0. So B1 is just the empty set. Okay, so there's nothing to correct yet. I haven't had any double overlap. Okay, so I'm just going to write this out. Let me write out the terms. We'll draw the diagram afterwards to make some sense. So I'm going to get probability of A1. That's the I equaling 1 term above. And then I'm adding to that. I'm going to get the probability of A2. And I'm going to subtract off probability of A2, intersect that B1, which only had one term, which was A1. This is my I equaling 2 term. If I go back up to this guy, I go I equaling 2. I'm going to have probability of A2 minus probability A2 intersected with B2, but B2 is just a union from 1 to 1 of A, in this case 1, so B2 is equal to A1, something like that, which is how I got that term. Then I'm going to add in the last one because there's only 3 terms. I only have to go through 3 terms in that sum. That's going to be probability of A3, and I'm going to subtract from that probability of A3, right, intersect B3, which is the union of everything up to but not including 3. So that's A1 union A2, something like that. That's the I equaling 3 term. All right, let's draw a big Venn diagram, then we'll be done with this thing to try to get an idea of what it is that this process or these set of equations are doing. So there's my universe. I'm going to go ahead and draw 3 events such that they might have some overlap. So I've got 1, 2, 3 things out there. Here's going to be my A1, here's going to be my A2, here's going to be my A3. I'm interested in getting the probability of A1, A2, A3 all union together. Okay, I'm going to do this a little bit in a shady way, all right? Well, okay, using shading, and I'm going to start out with probability A1. That is the A1 term. So I just go in there and I grab the first thing. I grab it like this, right? And I get all of that. At this point in the counting process, because I've only got one thing, we don't have to worry about any overlaps, right? Don't have to worry about any overlaps. The next one is going to do what? It's going to add in A2, but A2 has to subtract off what was common between A2 and A1. So I'm going to take A2, right, except for the part that A2 had in common with A1, right? So if I came in here and maybe used a little bit of a dotted line, right? Dotted line, this dotted piece right here, that little football shape, right? That is this piece in here, something like that. So I took all of A2 and I subtracted off that overlap. What did I basically do? This piece right here, right, was all the part of A2 that hadn't been counted before, right? So I took all of A2, but correct by getting rid of stuff that I'd already counted, something along those lines. And then if I go to the third piece, what do? I'm taking A3, right? So I'm getting my A3 in there, but I'm saying let's not keep or let's not double count whatever is in A3, but was also counted before from A1 and A2, something along those lines. So in this particular case, I don't want to count anything that was in A3 and also in the union between A1 and A2. That's that kind of dotted blue line. Everything in A3, but not including that kind of strange butterfly looking piece, would be this more solidy blue that I'm going to draw on here, something like this, right? So I find, right, the probability of the of the of the of the union of all these guys, PA1, A2, A3, even though they're overlapping, by just coming in here and adding them piece by piece, but not including the parts that I had already counted before, right? Just the other pieces. That's what this generalization formula does. I think that's enough for today. We'll pick up on this on the next lecture.